we're doing more with potential difference. So remember, that's just basically energy per coulomb. So just as kind of a summary, if you have some charge here, and I'm using capital Q for this charge, and we've got a point A over here, some distance R from Q. So first we looked at, or given this, the force on a charge at a point A is, so we could write that as FA, meaning the force at the point A, is just K, Coulomb's constant, times Q, big Q, because that's this one here, and little q would be whatever the charge actually is that you want to put at A. So if you actually put a charge Q here, that's how you would, down here, that's how you would calculate the force on that second charge Q. The field strength at that point, that's the part underneath here. So if you actually don't have a particle here, we're just interested in what is the actual field strength at that point. So we say, well, if we did have a 1 Coulomb charge there, right? So this basically just gives us the strength at that point. And the only difference is we divide through, we get rid of that Q, and that gives us the field strength at that point. And then we look at energy. So that's kind of the force side of it. And then if we want to look at energy, if a charge Q is at a point A. So once again, if we actually have a charge Q here, and it's a certain distance R from big Q, then the potential energy of that system, right, is just very similar to the force equation, just only R in the bottom and not R squared. And finally, the electric potential at the point A, which is the work required to move a +1 charge from infinitely far away to the point A. We could calculate that by using V like that. And I think in my original note it was a lowercase q, but since we're dealing with this big Q here, if we actually looked at the voltage, it would look, the graph would look like this. If Q is greater than 0. So the first part right here, right, this corresponds to, suppose big Q is positive, right? Well, that means we have to do work to actually get a +1 charge closer and closer to it. And so you would get a graph that looks somewhat like this, right? As R gets smaller and smaller, right? So this sort of corresponds to getting closer and closer to it. Then the potential difference would increase and increase. However, if it was a negative charge, right, it would go toward big Q. All, like if you had a +1 charge, it would go toward what I'm using big Q for here all by itself, right? You would actually have to do work to stop this. This is the system doing energy. And so you'd have what would look like that on the bottom, right? The potential difference would decrease and decrease and decrease. Okay, so now we can do the same kind of thing. So far, like I said, we've really just been looking at that one charge, or some point in space because of multiple charges. Here, we've got 2 charges, or I suppose we could have more, and we can look at all of the same things, mainly the change in electric potential. So if we have these 2 charges, which I've sort of just drawn here with these dots as Q1 and Q2, the electric potential energy between a pair of point charges, and basically just a pair of charges, is given right here. Right? Very similar, same essentially the same equation. And I probably, since these are both Q, I actually shouldn't write it like that, should I? I should probably write that as a little q. Right, we probably would write Q1 and Q2, because that's essentially it, right? That's the energy that you would have to put into this system, the work that you would have to do to set up this system. So if these were 2 positive charges, right, you would have to do work to actually bring them together. If the charges are initially separated by a distance R1, and then brought together to a final separation, R2, then the change in electric potential, or delta E, right, is just like anytime we're calculating a change. It's just whatever the final energy would be minus the initial. We can actually, this time I actually put in Q1 and Q2, and you can see those right there. So obviously below this, all I'm doing is factoring out the K and Q1 and Q2. So all of the numerator factors out of both because they're right there. And then we end up with this lovely equation down here, right? So it really is just about the distances. And once again, if you want to analyze, and this is the part, if you're doing a question like this, I would just think about, like, what do I actually expect? Is this a positive value or a negative value? Basically, if they're like charges, right, you have to do work to get them together. So I expect the energy to increase, right? The energy that's in this system is increasing as you do this work. And on the bottom, if they're unlike charges, right, it's doing this all by itself. You would have to do work to pull them back apart. So then that would be negative. Anyway, a couple examples. I already filled them in here just to sort of speed things up a little bit. But I'll go through the analysis just so we kind of understand it. So this first example, we have a point charge. I guess you might say a first point charge with a charge of 4 times 10 to the negative 8 coulombs is 2 meters west from a second point charge, right? So we've got the first one and the second one. First, we want to calculate the total electric potential at a point P, which is 4 meters north of what we're calling the first charge. So setting up this kind of diagram or whatever seems to be really key to this problem. And from there, you can kind of just do it with the diagram. You can say, well, I've got Q1 and Q2 down at the bottom, and I just wrote the values for the charges we were given. We're told they're separated by 2 meters, and the first charge was 2 meters west of the second. And then we're asked about the point P, which is 4 meters north of the first one. So it would essentially look like this. And then because I know I'm going to need the distance, in yellow here you can see I actually figured out what the distance would be between the point P and the second charge, right? Just obviously Pythagoras right there. I know the two sides of this triangle, so I can figure that out. And I just leave it as root 20. So I know that distance is root 20. I know the distance from P and Q1 I know is 4 meters because that was stated. So the first thing I want to figure out is the potential difference at that point P. I'm just going to use the principle of superposition, right? Whatever the voltage is there, or potential difference, I guess, it's just whatever the contribution is of Q1 plus whatever the contribution is of Q2. In both cases, I expect it to be positive because both Q1 and Q2 are positive, right? They were given to me as positive values, and negative should have been indicated. And I'm asking myself, well, what would be, like, what's the energy that I would have to exert, or how much work would I have to do to get a positive 1 coulomb charge to the point P, right? And they would be repelled by both Q1 and Q2. So I would have to do work in both cases. So these should both be positive values. I'll figure them out individually and then just add them together. So the way I could write that as an equation is over here. So V, what I mean by this is the voltage at, or potential difference at the point P is just equal to the potential difference from Q1 R1 away plus the potential difference for Q2, which is R2, or distance R2 away. And then I just plug in the numbers. K, you probably memorized it already, 8.99 times 10 to the 9. Put in the values for Q1 and R1, and then on the other one, put in the values for Q2 and R2, which I already found. Work that out. You could probably do that all at once in a calculator, and that'll give you 491.95 volts, or joules per coulomb if you prefer. Right? And then there's a part B here, calculate the work required to bring a third point charge, which has a charge of 2 times 10 to the negative 9 coulombs from really, really far away. So we can say, in theory, infinitely far away, to the point P. And, oh, there's my diagram again. So we already know the potential difference at that point. We just calculated it, 491.5, and that's the amount of work per coulomb. So if we have a 2 times 10 to the negative 9 coulomb charge, then the work is just Q times V. Right? Work that out, and we get 9.84 times 10 to the negative 7 joules. In other words, this is the amount of work that I would have to do if this system already existed, and we'll suppose that Q1 and Q2 are sort of fixed in this arrangement, 2 meters apart. If I wanted to take this third charge, which is 2 times 10 to the negative 9 coulombs, and bring it from far away and put it at that point P, then I would have to do 9.84 times 10 to the negative 7 joules of work, right? That's what I would have to do. And at that point, when I leave that charge there, that's how much more energy this system would have. The second example is worth, like I said, conceptually, just like understanding what's going on and making sure, yes, that's what a solution should look like. We've got two particles, a proton, which we probably know by now has a charge of 1.6 times 10 to the negative 19 coulombs, and a mass of 1.67 times 10 to the negative 27 kilograms. A lot of numbers to remember here, I guess. And we have an alpha particle, which is just a helium nucleus, or regular helium, you might even say. And so the charge is just double the charge of a proton, because a helium nucleus would have 2 protons and 2 neutrons, and the neutrons would be neutral. And the mass, roughly 4 times the mass of a proton. So they're separated by an extremely large distance, so, for all intents and purposes, they're infinitely far away. They approach each other on a straight line path, so basically they're headed right at each other, both with a speed of 3 times 10 to the 6 meters per second. We want to calculate the separation between the particles when they are closest, right? So we basically say these two particles, here's our proton, and here's our alpha particle. I'll make it a little bit bigger, and they're both going with V and V. So when they're really, really far away, they've got kinetic energy. Again, we can obviously ignore gravitational potential energy or anything like that. As I've said, it's pretty insignificant compared to electric potential. But definitely with these speeds, you could consider the kinetic energy. So they're headed towards each other. They both have kinetic energy. And technically the electric energy of this sort of system is 0 because they're really, really far away. So as they get closer and closer, though, they're putting energy into that system because they're getting closer together, right? We've got two things that are technically both positively charged, right? So that means energy, the energy is increasing in that electric field as they get closer and closer together. So we can look at that, and this is just, again, written right out there. Initial energy equals final energy. We know that. So in other words, the kinetic energy of the alpha particle plus the kinetic energy of the proton plus the energy that's in the field initially equals the sum of all three after. And again, we can ignore any other types of energy such as gravity or whatnot, although we could assume also that this happens at the same height. Initially, because they're really, really far away, the electric energy in this field is 0. And when they're closest together, right, we'll assume sort of for that instant, both of them have essentially stopped for an instant, right? They're closest together, and then they're going to start moving away again. So that means at that instant in time, both of their kinetic energies are 0. And that leaves us with only those 3 terms. We can just plug in the numbers here. So 1/2 the mass of an alpha particle times that velocity plus 1/2 the mass of a proton times its velocity equals the energy in this system, or electric potential energy. Underneath, all I did here was factor out, because the V's are the same and the 1/2 is in both terms. I just factored the V squared over 2 out, and that leaves me with just the sum of the two masses on the other side. Then, since we want R, essentially you multiply both sides by R so that it cancels out here, and then divide both sides by this sum of their masses, so that gets it down on the denominator on the other side. Multiply both sides by 2 and divide both sides by V squared, and that will get you to end up with what's underneath. R equals 2k times both their charges divided by V squared and sum of both their masses. Put in all those numbers and presumably punch it into a calculator, or take 10 minutes to work it out by hand, whichever you prefer, and you get R equals 1.23 times 10 to the negative 14 meters, which would be, or 12.3 femtometers, a femtometer being 10 to the minus 15 meters, if you prefer. So very, very, very close. This is, the typical distance, or less than the distance of, like, say, a proton or something like that, if you were estimating about how much space it would take up or whatever. We'll get to quantum mechanics and all that later, but very, very close. Huh?